booth. Okay, we're good to go. All right, so after today, we'll be more than halfway done with the tutorial. I don't know if you yet feel like you've been hit by a bus, but that's kind of how people often feel with all the information. There are a few things today, so I'll go over the schedule in a minute, but I just wanted to point out, and I'll have this up during breaks, we have both Meet a Scientist and the Mesa Lab tours today, if you're interested in that. So I put the folks who are doing the tour, that's over here. It's from 12 to 1, and you just meet in this front lobby area where we met before the picture yesterday. And then the folks who are doing the Meet a Scientist, I have your names here, the different rooms you'll be in, and the admins are going to be, and I will be around to help get you to those rooms. And we're going to try to put signs on the doors. That was some feedback we got yesterday that would be helpful. So we will do that. And if you have any other questions about that, let me know. So this is today's agenda. We're kind of going back to the atmosphere. I have some cloud socks today and my cloud earrings and lots of blue. Whether it matches or not, I don't know. My children picked it out. So we're going to learn more about above the troposphere, so the whole atmosphere community climate model, and then also about chemistry and aerosols. And then again, there'll be the second morning break, we'll have food. I think we have it set up so that hopefully people can get through the line. It seemed like there was enough yesterday and people got through faster, so that's good. We'll have the first lab session this morning. Who was able to get through the queue last night for their long simulation? Looks like a lot of people. Okay, that's great. So if you got through, great, and if not, we'll try to submit today and get through before tomorrow, because that's the day that we're going to use some of that output. And today's exercises don't depend on yesterday's, so you can, even if you're still in the queue for that or you submit it today, you can still do today's stuff and not have it depend on yesterday. All right, and then, like I said, at lunch, there's Meet a Scientist. This is from 12 to 1. We are expecting that you get food and then you'll eat while chatting in your small groups. You could eat beforehand if you don't want to eat in front of a group. And then if you are doing the Mesa Lab tour, this is with the science education, so they're going to take you through the exhibits and just talk to you about all sorts of stuff that is done at NCAR. Please make sure that you leave the practical session at 11:30 and get a chance to eat, because you won't get a chance to eat during the tour, and we want to make sure that you don't just completely collapse during the afternoon session. The lecture this afternoon is about sea ice modeling, so that's what I do, but I'm not giving the talk because I have enough going on this week, so my colleague will come give it, and then we'll do more of the lab exercises. And I wanted to point out, some people asked about a volleyball. Someone is bringing a volleyball for pickup volleyball this afternoon, and I meant to bring a Frisbee, but this morning was absolute chaos at my house, so that didn't happen. But maybe I'll bring a Frisbee tomorrow for you, if anyone wants it. The website, this is the same as always. And I just wanted to, so starting tomorrow, we're doing diagnostics. You can run the diagnostics for all of the different components, but we were going to initially break up the groups depending on what component you're most interested in. And so, and then on the last day, we do challenge exercises, and that again will be kind of by component. It's not that you can't do other ones, but at least initially, we want to kind of group you by the component you're most interested in. So I just wanted to get a quick show of hands so that we can try to assign different groups to different rooms that are about the right size. So if you think you're interested in land ice, glacier, ice sheet modeling, can you raise your hand? Okay, pretty small group, that's fine. That's kind of what we expect. How about sea ice? Can you raise them like high? All right, okay. The land model, CLM, CTSM. Okay, ocean. Okay, and then atmosphere, and so that's CAM, CAM-CHEM, or WACCM, any of those. Okay, this is about what I expected. We just want to check, because if suddenly like half of you wanted to do land ice, it would be like, whoa, what is happening? So not that it's bad, just most people, there's a smaller community for that, I guess I should say. All right, so without further ado, I'm going to go ahead and open today's first talk, which is by Nick Davis. Okay. So Nick is a scientist in the Atmospheric Chemistry Observations and Modeling Labs, or ACOM, so not in the Climate and Global Dynamics Lab, which is in this building. He works on dynamics of the atmosphere and in the whole atmosphere community climate model, WACCM, but he is soon going to be leaving NCAR for other adventures, and so at the end of this, he's going to give you some other contacts for people you could be in contact with who would probably respond more quickly.
Okay. Thanks, Alice. This is the first time I've been to the tutorial and first time I'm giving the talk, but imagine it's everybody's first time with the tutorial here, so I'm not too worried if I screw up. Yeah, I'm gonna talk about a different sort of perspective of the atmosphere, and one that goes much, much higher than probably what you've been thinking and talking about the last couple of days. So I've got a schematic on the left of the atmosphere, and so we've got the troposphere, which is very, very tiny here. This is in altitude here, so they've got miles and kilometers, and then there's the stratosphere, and the ozone layer is set off with this sort of like little yellow strip. The mesosphere from 50 to 80 kilometers or so, and then we enter the thermosphere where you get things like meteors and auroras, and then finally the exosphere where you have low Earth orbiting satellites and things like the International Space Station. And so this is just referencing the finite volume model, but sort of these altitude change, these model lid heights have changed a bit as we're updating the model, but the sort of CMIP6 versions of CESM CAM had a lid at about 45 kilometers, so somewhere kind of right near the top of the stratosphere. WACCM, which I'll talk about today, has a lid around 140 kilometers, so into the thermosphere, but still pretty low when you consider that WACCM-X goes well into the exosphere. And this is just a blow up of this little strip showing you usually all the things we're interested in, like clouds, where do weather balloons reach, where do aircraft fly. There's no UFOs on this picture yet, but probably in another 10 years there will be. And so, the way we do the atmosphere configurations really is we've just got progressively higher model lids. And they're actually chosen for a reason at these levels. There's reasons why we sort of choose, for example, 140 kilometers, which I'll talk about in a little bit. But as you go up with higher lids, you require new and more comprehensive physics in your atmosphere. So you can imagine by the time you're getting to the aurora zone, you need a lot of interesting high energy physics to reproduce that kind of variability. And the focus of the talk that I'm going to give you today is really just, what physics do you need to resolve the atmosphere up to about 140 kilometers? Why does this part of the atmosphere matter? We have jokingly referred to it as the ignorosphere sometimes because people just don't like to think about it, but we'll talk about why you may want to consider it. So why run this model, and then how does this model perform? Obviously, making a deeper atmosphere with lots more stuff costs more, so we'll talk a little bit about that. So similar view, a little shorter now. We're only going up to 120 kilometers, so just the lower thermosphere here. This is a plot of temperature now, degrees C in Fahrenheit, again with miles, kilometers. And so you can see, pressure here is written on the right, and so it's dropping exponentially with height. That's sort of just, we all expect that behavior, but you can see very quickly by the time you get to, say 100 kilometers, you are very, very rarefied air is what they like to say. So very, very low pressures. And temperature really has a characteristic lapse rate in each sphere. That's why we've given the spheres a name, is because there's a characteristic temperature profile, and that sort of defines a lot of the interesting behavior. So in the troposphere, the lapse rate's really set by convection and some sort of radiative cooling processes, and so it tends to fall off on something like the average of the moist or dry adiabat, okay? But then in the stratosphere, it turns around. It's set by the absorption of sunlight by certain radially active gases, some ozone photochemistry, so there's some reactions that actually contribute to heating of the atmosphere. And so the stratosphere is very stable, hence the name, it's very stratified, so temperature increases with height. So vertical motion and convection, you don't get convection in the stratosphere. It's a very, very stable system. I will talk a little bit later, though, that doesn't mean it's not interesting. When you do actually get some weather in the stratosphere, it's really, really violent. The mesosphere flips again. You get reduction of temperature with height, which is really there's just less and less absorption by gases, partly because the gases are at such a low density, and also you get a lot of infrared cooling to space. And so this is a region where essentially with height, you're just getting to the point where there's just not much energetically going on in terms of absorption and emission. And actually the coldest point in the atmosphere is not the tropopause, it's the mesopause. The summer mesopause is super cold. It can be below 140 Kelvin. So usually we think of the cold point in the tropical tropopause layer being somewhere, north, like 60 to 80 K north of that. So this gets pretty cold. And then the thermosphere, it flips sign again. And that's really set by the absorption of high energy sunlight. There's a lot of very, very high energy UV and even higher, sort of shorter wavelength radiation going on up there. And then layered on here, we've got auroras in the thermosphere. So you've got a lot of energetic particles. There's some magnetospheric influences from the upper atmosphere where the magnetized part of the atmosphere and the neutral part of the atmosphere, which again is what most of you are probably thinking of, the WACCM folks call it the neutral atmosphere, interact, and then meteors are actually reaching down into the mesosphere and doing a lot of interesting things chemically. So when meteors fly into the atmosphere, friction starts stripping off lots of metals and other things, and there's actually metal layers in the mesosphere that have some interesting and important chemistry. And if you're an astronomer, you'll know about them quite well. There's another pause in the system. There's a tropopause, stratopause, mesopause. There's also the turbopause. That's not related to temperature structure. That's actually where you can't make the assumption of an ideal well-mixed gas anymore in the atmosphere. So it happens that roughly coincides with the mesopause, where basically eddy mixing of Earth's atmosphere, which keeps all of the different gases of different weights well mixed, is roughly in balance with molecular diffusion. So basically the gas is doing their random walk under the influence of gravity. And below that, we make the assumption that the atmosphere is well mixed. Roughly everything is oxygen and nitrogen are well mixed and they have roughly the same percentage at each altitude. And above that, it gets interesting because lighter species become progressively more dominant with altitude. So you get basically like a gravitational separation in the atmosphere. So if you run WACCM, it is not assuming well-mixed gases past this level. So you can see what I mean by the physics start to get more complicated. We've also got the ozone layer, which is roughly in the middle and lower stratosphere, and the ozone hole, which I'll talk about a little bit later. Air glow, which is spontaneous emission by the atmosphere, sometimes emitted by the minerals stripped off from meteors. So if you're an astronomer, you know that there's a certain background air glow at night, which means that the night sky is never actually completely devoid of light. So the atmosphere actually has layers that are emitting in the mesosphere. Like I said, auroras, which are charged particles precipitating due to space weather. And then talk a little bit about aerosols from things like volcanoes and wildfires that when they make it up into the stratosphere can have long residence times and really long climate impacts. So what's the motivation to run this complicated model? So this is an image that's been shared by Mary Barth a few times. She's in M-cubed and ACOM, sort of showing how time and space scales tend to project along a nice line in terms of our modeling suites. So you think of things like an LES model as sort of short time scales, short space scales. WACCM is one of the models that's generally up on that further right side, where we're really worried about things on the sort of century climate scale, maybe down to, I would argue, days and weeks. It should be down to there as well. But certainly also, yeah, on the regional to global scale. The important thing, if there's one thing you can take from this talk, is that the middle atmosphere, so the stratosphere and the mesosphere, is really a coupling zone. And it's a coupling zone in the vertical, across space scales, and across time scales. When we start talking about stratospheric and mesospheric dynamics, we're worried about everything from gravity waves, which have time scales of minutes, and space scales of tens of kilometers, to large planetary waves and tides that have scales and time scales on the order of days and the whole planet. And so I really want to emphasize it's microscale to planetary scale. We just talked about molecular diffusion being a really important process. Microseconds to centuries. Chemistry and photochemistry is really fast, but it also has really long time scale effects on the atmosphere. And it's really a nexus of chemistry, aerosols, circulation, and radiation, more so than I think the troposphere. And that's from a person who started with tropospheric dynamics in grad school. This is a really incredible place where a lot of different processes interact. So we really need a model that can simulate coupling on short and long time scales. Because we're running a global model, we're probably not going to be running WACCM as an LES, but we really need to unite those timescales a bit. So this is just some further motivation. So on the left, this is a plot in the vertical with potential temperature coordinates. This actually is going up pretty high through the stratosphere, if you're not familiar with how to convert those. But it's chosen basically isosurfaces of, I think, potential vorticity. So basically, the rotation of the atmosphere. And so this is showing the polar vortex during a really disturbed state 2 years ago that preceded a lot of extreme cold weather in the US, especially in Texas and the Great Plains. And so polar vortex and its variability are windows of opportunity for weather forecasting and subseasonal forecasting because they tend to be connected to sustained surface impacts, including cold air outbreaks. I'll talk a little bit about all these later in applications in more detail, but climate geoengineering is sort of a new area of study, and one of the important ones that sort of WACCM has a lot of use for is using stratospheric aerosol injection, where you basically put aerosols into the lower stratosphere to try to reflect sunlight. So there's a lot of interest in how effective could this be, what are the unforeseen consequences, things like that. And then, of course, ozone depletion, where human emissions of CFCs led to enhanced ozone loss at the poles and resulted in essentially a full depletion of ozone, especially in the southern hemisphere pole. And I'll talk a little bit about how it's not even the final story yet on the ozone hole and its recovery, in part because of some of the results that have been generated by WACCM. So you've probably seen a million plots like this, these schematics, but WACCM is really no different than CAM in a way. They're just the atmosphere component of CSM. So anything CAM can do coupled to all of these different models, WACCM's going to do. And essentially, in the last CMIP, there were CAM and WACCM simulations that were fully coupled and used to sort of understand or at least characterize projected climate changes under different forcing scenarios. So WACCM is just the same part of the party. It's just a different flavor with different physics in the end. So this is the detail slide, and I apologize for all the detail, but part of it's because I would forget a lot of this stuff too. WACCM basically inherits a lot of the stuff in CAM. So it's got the same convection schemes. In the new version of the model that's being developed, it's even got the same vertical level scheme in the troposphere and stratosphere. And so really what WACCM's trying to do is build on top of what CAM is. But it goes to 140 kilometers, so 6 times 10 to the minus 6 hectopascals. It's pretty thin air. With 70 or 110 vertical levels. So there's a lot of detailed neutral chemistry, and we have 2 schemes. One is this middle atmosphere scheme, which basically means it's enough to resolve the stratosphere and above, but you wouldn't use it to study air quality or something like that. It doesn't have all of the important, for example, organic chemistry and other processes that you would want to do something like that. And so then there's another scheme, which is TSMLT, so troposphere, stratosphere, mesosphere, lower thermosphere. That's the everything scheme. That's about as complicated as it gets. There's a lot of species, hundreds of species, hundreds of reactions, and it's a bit expensive to run. So you've also got aerosols. There's prognostic aerosol schemes for the troposphere and stratosphere. There's ion chemistry in the MLT region that gets turned on at a certain altitude, with a lot of higher energy physics, including things like ion drag and the auroras. There's extreme UV and non-LTE radiation. So your normal radiation schemes assumes local thermodynamic equilibrium. We can't do that when we get in really thin air in the upper atmosphere because things can. I'm not a great radiation person, but I will just say we even are worried about things where chemistry, like certain compounds will absorb radiation, be transported thousands of miles, and then start emitting it again. And so we basically can't assume everything's in perfect balance all at the same time in the same box. Gravity waves become really important, and I'll talk a little bit about that too. And then the quasi-biennial oscillation. So WACCM's one of the few Earth system models that can simulate an internally generated QBO, which is driven by wave forcing. Again, molecular diffusion and constituent separation, and then this thermosphere extension to roughly 600 kilometers gives you WACCM X, which the X stands for extension. And this is just a quick plot of WACCM versus WACCM X. I don't want to go into too much detail except to say, WACCM X is higher. They're similar horizontal resolutions, but you get different schemes. So WACCM X is really run with MA. You're not going to do air quality with WACCM X going up to the exosphere. That's probably not what you're going to use it for. There's different sort of radiation schemes and things. The only thing I want to draw your attention to is, WACCM X has a lot more high energy physics built into it because you're going to be studying probably things like space weather. So you're going to need those kind of physics. So gravity waves. There's different gravity wave schemes. Gravity waves are really generated when the atmosphere undergoes some sort of disturbance from balanced flow. So things like flow over orography, which those waves tend to primarily affect the stratospheric vortex. Frontal waves, so you have a weather front move through that really disturbs geostrophic balance and kicks off waves. And then convectively generated waves, so you have a lot of latent heating, which creates, again, a disturbance to the flow. And gravity waves are really a way for the atmosphere to come back into balance and create balanced flow. There's a lot of schemes, and they all have a very important impact on the middle atmosphere. They're sort of a first-order process in setting the structure. So one of the reasons the mesopause is so cold and is in the location it's in is because of gravity wave forcing. So it's interesting. We're far up 100 kilometers away from the surface, but convection and fronts and the little ripples at the surface in orography really start to matter a lot. Again, there's a lot of vertical coupling. This is showing you the QBO, so if you haven't seen it, in the tropics, there's these descending westerly and easterly anomalies right on the equator with a period of about 28 months, so it's not an annual cycle, and it's driven by wave forcing. Basically, waves with different phase speeds propagate up and start pulling these anomalies down one after another. 110 level WACCM does a pretty good job of simulating the descent of the anomalies. But when we go to 70 vertical levels, it starts to get a little dicey, and we don't get much propagation below the middle stratosphere. And so again, it's a higher model. You think, okay, you probably don't need high resolution, but you do. You need 500 meter resolution to actually get a good QBO in the stratosphere, which is pretty high resolution when you're considering that the stratosphere is from 10 to 50 kilometers. So what does the atmosphere look like in this region? This is from WACCM 6, 70 layer, using the finite volume dicore for DJF and JJA, showing you temperatures and zonal winds. The temperatures saturate because, again, it's the thermosphere, so stuff gets really hot. The fun fact about that is because the air has such low density, there's almost no thermal conductivity. So you could be in 1,000 degrees and you might not even notice it up there. So we've got the troposphere down here at the bottom. It's relatively warm in the tropics and cool in the mid-latitudes. Then there's your cold point tropopause and your polar vortex in winter here. And then the stratopause is a relatively warm region. Here's the mesopause in each summer season, which again gets down to about 140 Kelvin, so very, very, very cold. And you can see that the familiar tropospheric jets are down here, but then in the stratosphere it's kind of fun. We have westerlies in winter and easterlies in summer. So we have got flipped jets in the stratosphere, because if you look over here, you've basically got one pole-to-pole temperature gradient in these regions. and then the jet slip sign in the mesosphere and lower thermosphere. I will say the southern hemisphere jet just tends to be a lot stronger. What does ozone look like? This is total column ozone. So Dobson units are basically like if you took all the ozone in the atmospheric column and collapsed it down to the surface at standard pressure. So it's a column measure. This is integrated, but most of it's coming from just that narrow ozone layer in the stratosphere. And so let's talk about the bottom first. This is from a satellite instrument, and these are just from 1 year, so a single year. So there's a lot of variability baked in here. But what you see is so this starts in like January 1st and goes to December. So you see really high ozone in late winter and early spring. In the northern hemisphere, basically ozone has been piling up and getting pushed towards the pole by the residual circulation in the stratosphere, which is basically this fountain that carries air from the tropics to the poles. And so ozone gets piled up in the winter into the polar vortex. And then as the sun returns to the pole, different catalytic loss cycles start eroding the ozone. And by the time you're at the end of summer, early fall, you've really chopped away at the ozone you started with. In the northern hemisphere here, you reduced it by a factor 50% or something. Southern hemisphere, same thing. You've got high ozone here at the start or at the end of the winter, but you can see that it's much weaker and it tapers off much quickly to almost nothing by the time you get to fall. And you can see that WACCM's basically simulating a lot of the similar features here. So we've got that northern hemisphere spring maximum, southern hemisphere spring maximum, and of course the ozone hole. So there's almost no ozone right over the pole. And so to get ozone, you really need temperatures to capture the right chemical reaction rates, you need the right chemistry, the right emissions, and you need circulation transport. So nailing stratospheric ozone and trying to understand the ozone hole really requires a model of this complexity. And again, this shows you the ozone hole now integrated over the South Pole in spring and then the North Pole in spring. And so this is different flavors of WACCM, the historical simulation, AMIP simulation, and then SBUV is another measure of total column ozone. And so you can see the ozone hole starting in the late 70s and then bottoming out sort of in the 90s and then some sense of recovery. One thing though that's important when we do these chemistry studies is natural variability in the model affects chemistry because it affects transport, affects reaction rates, things like that. And so one of the things we can do is actually nudge the model towards some kind of observational estimate of observed variability to remove that uncertainty from the projections. And when we do that, which is this purple line, you can see that the model simulations much better match observations. And so the difference between the purple line and basically the blue line, the blue dots, is the influence of the circulation. So the circulation plays a big role in things like this. Does the middle atmosphere matter for the surface? Yeah, kind of. So this is the interannual standard deviation of sea level pressure in, I think DJF. Observations on the upper left, WACCM in the middle, and then CAM on the upper right. And CAM's a bit too variable. And we think that one of the reasons that WACCM is a bit closer to reality is because the stratosphere tends to have longer lifetimes, longer timescales of variability, and it can really link those stratospheric anomalies to surface weather regimes and give you actually less variability and more sort of prolonged weather regimes. So if you're familiar with how things like the polar vortex can influence surface weather, that should sound familiar. Okay, ozone depletion. This is a complicated plot, but there were some folks at NOAA a few years ago who noticed that the rate of change of CFCs concentrations in the atmosphere, it was dropping, so it was negative, so rate of change, so CFCs are decreasing year by year, and in red here's the OBS, and then they stopped decreasing so fast, which means that probably someone was emitting CFCs illegally under the Montreal Protocol. And so they used a lot of different models, including things like box models, but they also used WACCM to try to understand whether variability, again, in the circulation could be implicated in the slowdown in the decrease of CFC concentrations. And basically, like, there's a few places CFCs are still being emitted from, like old refrigerators and stuff. They call these banks. But basically what happened was they looked at these runs and said, when we run with just natural variability, we don't see any increase. But if we run with enhanced CFC emissions, we do start to match the observations. And it turned out actually there were some rogue factories in China, and China cracked down really hard and shut those factories down, and the emissions have since returned on their decline. Polar vortex impacts, so this is kind of my area of work. I really like to understand how the polar vortex influences surface weather. So this is showing you the standardized polar cap geopotential height. If you're familiar with the northern annular mode, just take the negative of this. Basically, it's where is the jet essentially meridionally at each level. And so, this means the polar cap is very warm. We had a sudden stratospheric warming on this date, and this is from MERA 2, and then some forecasts run using WACCM. And so you can see in observations, it looks sort of like there's this downward progression occasionally where these warm anomalies bubble down to the surface, and you can see that you get this sort of sustained pattern of basically a warm polar cap at the pole. We used a set of model simulations where we let the initial conditions in the forecast drift in the troposphere and stratosphere, and actually showed that rather than downward coupling, actually what's going on is that the stratosphere and troposphere feed back on one another and tend to reinforce the circulation anomalies in one another. So again, if you're wanting to understand subseasonal forecasting and surface variability, you really need a good stratosphere to understand the sort of sustained variability you get in the wintertime. A little bit more about subseasonal predictions. So this is some anomaly correlation. So high means that the model forecast did a good job. Low means they did a bad job. This is subseasonal prediction. So this is looking at the NAO predicted by a set of models. So WACCM in blue, and then, CAM in the pink and red. And CAM in the pink is sort of comparable to WACCM in blue because they are a similar set of ensemble members. And then the gray and the black lines are ECMWF and then NOAA. And so actually, if you look, we're about comparable with CAM and NOAA at week 1 to 2, but by weeks 3 to 4, which is really that subseasonal window, WACCM's got an edge over a similar ensemble size of CAM in predicting the NAO. Again, just highlighting that a lot of the variability at the surface is tied to feedbacks with the stratosphere. And actually, CESM 2 and CESM 1 do better than NOAA at this kind of predictability. Even out, weeks 5 and 6, if you want to believe those forecasts. Finally, geoengineering. So yeah, the idea is you inject basically stratospheric aerosol into the lower stratosphere, and it can reflect sunlight, which can sort of potentially act as to counteract a lot of greenhouse gas-induced warming. So this is showing you, the surface temperature response in your normal sort of CMIP simulations, and then with these different geoengineering simulations. And you'll see that it's not as red, but it's not zero. It's not this sort of like all sort of tan and light blue color. WACCM is one of the few models that's really equipped to study this, but there's a lot of regional sensitivities and maybe adverse effects that need to be studied. And again, this is where a lot of, I would say even, I think private sector interest is, and WACCM is one of the main models for that. I'll just summarize because I'm running a little low on time and say folks have used WACCM to understand why wildfire smoke from some of these big wildfires, like the Canadian wildfires in 2017, got to the stratosphere and stayed there for like almost a year and continued to have a radiative effect on the surface. And it turns out you actually need an assumption of a certain amount of black carbon on the aerosols, which acts to heat the aerosols, which allows them to continue to rise by absorbing sunlight into the stratosphere. And folks have used WACCM coupled with CARMA, which is a really sophisticated aerosol model to understand that. So okay, why would you want to run WACCM? I mean, basically, yeah, it gets a greater vertical extent of the atmosphere. It resolves prognostic chemistry and aerosols. It has middle upper atmosphere physics. It's got really good vertical coupling. A lot of the scientific questions that we're dealing with and that I've just showed you are at a nexus of multiple disciplines with a lot of coupling across time and space. And WACCM is really a cross-lab thing. It's not just an ACOM. There's a lot of folks in CGD and HAO and external, from the external community that use and develop this model. It costs more than CAM. So if CAM costs 3,700 core hours per simulated year to run, WACCM in its good configuration costs somewhere to around 22 to 30,000 core hours per year, so it is not cheap. But we have an economic configuration that's run at 2 degrees with MA chemistry that's almost as cheap as CAM, and it does pretty well. So we're aware that our model is crazy expensive, and because of that, we are always dedicated to carrying a more economical version that the community can use. And actually, I use it because I want to do so many simulations. There's no way I could use 1 degree TSMLT all the time. This is just to say it's not much different. If you just look at the right, this is a climate sensitivity plot, global mean surface temperature versus TOA flux, showing you the climate sensitivity to a doubling of CO2 of these different configurations. So full-blown chemistry, middle atmosphere chemistry, and then 2 degree middle atmosphere, they all have about the same climate sensitivity. And so they're really pretty comparable unless you've got a very niche reason to run with slightly higher resolution or slightly more complicated chemistry. I don't want to belabor the point with these kind of plots except to say, yeah, you can run with interactive or specified chemistry, which obviously saves you a lot of computing time. You can run with a free running atmosphere, or like I've said, these nudging simulations where you constrain the variability to some known historical patterns, which is really useful for doing good science, which is what I'm talking about here. So it's basically you nudge the horizontal winds and temperatures to a reference value. So it's like an extra relaxation term we put in the model. And it could be a reanalysis, or it could actually be another CESM simulation. So you can imagine that you can start doing fun experiments if you constrain the atmosphere from one simulation to another, but then change something else. Again, it eliminates a lot of the uncertainty due to atmospheric variability, and we've gone through the rigmarole to basically understand the scheme and what parameter settings you should use. And so if this kind of thing interests you, there's a lot of folks in our group who would be happy to help. And yeah, future development, you may have heard, I'm not sure, there's a new die-core, the spectral element model that we're working on with, for WACCM, 135 vertical levels, so everything keeps getting more expensive. But that's really to help us better resolve boundary layer processes with CAM and also better resolve some of the middle atmospheric processes. So we've actually beefed up the vertical resolution in the middle atmosphere. And this is just showing you comparisons with SABRE of the June zonal mean temperature. So SABRE is a satellite product that has coverage pretty high in the atmosphere. And so our old model had biases on the order of 30 Kelvin relative to SABRE. And now some of the candidate models we've got have biases on the order of like 5 to 10 Kelvin in the middle and upper atmosphere. And we're really working on reducing all the sort of biases in a lot of these processes. And so I think there's been growing pains with spectral element, but I think it actually looks like it's going to be a really amazing new model. So I just want to leave you with contacts for WACCM and group membership in WACCM. It's not superficial. Simone straddles so many different research groups at NCAR. I feel bad putting her name here, but she's super involved in WACCM. So like Alice said, I'm going to be leaving soon, but Simone and Doug, I would say, are some of the great chemistry contacts and application contacts in the WACCM group. And then I've put down here folks from HAO and then one of our external people these people all use the model. They all use different flavors of the model. They're always happy to help.
All right. Thank you so much, Nick. All right, so like usual, I'm going to run around.
Thank you very much for this great presentation. I like this model a lot. especially this is the first time I know about it. But I don't know what boundary conditions that we could use to run the model, and especially if we are going to apply for a specific location, say United States, for high resolution. How can we do that, and how much time needed to run this case?
You mean like regional refinement
Yeah,
over the
regional
US?
or local, because I see this is one degree. This is the highest resolution. If we are going to study for a specific state, for example, and we need higher resolution than 1 degree, is this capability also in the model or not?
Yeah. Using this, it's sort of like CAM where you can do so it's a global model, so you don't need boundary conditions except chemistry emissions basically at the surface, and that's always built into comp sets when you run these models. So I've run WACCM with regional refinement using the spectral element core. I don't have to chase down any boundary conditions, but it's a global model, and if you regionally refine something, you have to run the whole model at the very fast time step needed to get fine resolution. And so you're talking hundreds of thousands of core hours per simulated year. That said, people do use it to study gravity wave dynamics. They'll do regional refinement over the Andes or even over a place like the UK and run WACCM globally to try to understand what's the response of the atmosphere to just the gravity waves resolved over that region. But yes, it is super expensive, but there's also comp sets so that from a user perspective, setting it up isn't that bad.
I'm asking because if one of my students is going to do his dissertation based on this model, how can get access to supercomputer here at INCAR, because we don't have this.
Oh.
So this is very important because of our students.
All right, hold on 1 second before the next question. So the question is, how do we get access to the supercomputer? If you're at a university, you can get university allocations, and if you have an NSF grant, you can get an allocation. We were planning to talk about that Friday, like how to get access to the supercomputer, because as you're saying, you really need a supercomputer to run something like this. So we'll talk about that more. Nick's not necessarily the right person to answer that question.
Thank you for the very nice presentation. I have two related questions about aerosol processing in WACCM.
Sure.
So for the particle size distribution, does WACCM use like a bulk scheme or like a size resolved scheme for the aerosol? And the second question is, you mentioned the Karma aerosol module. Is that already fully coupled in WACCM or for public access or not?
Simone says next talk.
All right.
Yeah, you're going to get more details on the chemistry side from Simone very, very shortly. Yeah.
Okay, next question.
Hi, thank you for the talk. It was very nice. I'm wondering if you're looking at dynamics that are kind of right on the edge of this 40-kilometer, like I'm thinking Brewer-Dobson circulation kind of thing, do you think it's worth it to use WACCM for something like that versus CAM?
Yeah, certainly. So if you're talking about FV, finite volume, with a 45-kilometer lid, CAM's not even resolving most of the stratosphere because the sponge layer starts in the ozone layer. So if you were running CAM or something to actually get some kind of ozone layer, yeah, I would, for sure with finite volume, you need to use WACCM to study the Brewer-Dobson circulation. It's kind of up in the air with these new places we're going where we now have a mid-top model in the future with SE that's going to be at 80 kilometers. That may have a pretty good Brewer-Dobson circulation. We don't know yet. But for sure, if you're doing middle atmosphere stuff, including just the stratosphere, I would use WACCM. Yeah, for sure.
All right, who else has questions? I will make a comment while you maybe think of other questions. So if you use something like the CMIP archive, you will see that there's CESM2 simulations, some with WACCM, some with CAM. And that's what Nick was talking about. Some of the simulations have been run with WACCM, so the full model, and we submitted those, and some are run with just CAM. And I know that there was a lot of discussion within the CESM co-chairs meetings, and you'll learn a little bit more about all the governance on the last day as well. I mentioned it the first day too, about how many of each ensemble we want to do, because we're always resource limited. Everyone wants higher resolution, they want more ensembles. You know, it's never like, oh, we have enough. There's always more. All right, other questions about WACCM?
Just a quick question, maybe missed that part. Do you have any ensemble for the S2S prediction set for new WACCM X, or just only you have WACCM 6 S2S?
Yeah, we just
And
yeah, we just
is there
have
any, yeah.
WACCM 6. Here, let me pull it up. You're talking about this. So, yeah. Sorry, the question was.
Yeah, I saw that plot we have WACCM 6 S2S prediction dataset.
Yeah.
Do we have also a dataset for the WACCM X? I mean, for
Oh,
the,
no,
yeah,
no. There's
Nothing.
not. I'm not aware of an S2S for WACCM X. I know Nick Petitella looked at some of the like upper atmosphere effects in the WACCM 6 forecasts, but yeah, no one's done the sort of full WACCM X stuff yet. Yeah.
So have you ever checked like for the some case-based event comparing with the WACCM 6 and WACCM X, for example, atmospheric river or transportation of moisture or maybe heat wave for the S2S events? Or
I
is
mean,
there any differences or?
Yeah, I've compared WACCM and CAM just because it's sort of off the shelf for us here because we have like the real-time systems for both WACCM and CAM. It's a mixed bag, I would say. I know for the cold air outbreaks, a lot of the time WACCM tends to be a little bit better, and we think that's because of this strat-trope coupling. So actually, when we look at this kind of plot in WACCM versus CAM, this tends to not look so much like MERA2 in CAM as in WACCM. So at least WACCM versus CAM, we've done comparisons, but higher than that, no. Yeah.
Thank you.
Yeah.
I have another question about the vertical resolution. You said the WACCM can simulate QBO due to its high vertical resolution. Just curious whether we can adjust the vertical level in WACCM.
Yeah, I mean, you can always do that. There's a CAM build option called nlev, and you have to rebuild the model and tell it number of levels, and then when you initialize the model, you just have to have made the right A and B hybrid coefficients and all that, and interpolate everything for the model. And if you did everything right, it'll work. You can always run with any arbitrary vertical levels. You just obviously have to know the tunings will be off potentially. So like one of the things we tune for the QBO is how efficiently convection kicks off gravity waves. And that's slightly different depending upon the level scheme because the efficiency means something when your vertical level scheme is like that versus that. And so I will just say like you can do that, but you got to be like mindful of the tuning going on. Yeah.
Thank you.
All right, other questions?
Hi, thanks for the great talk. So I'm wondering if WACCM has been used in any paleoclimate context or if it's mostly just for the present atmosphere.
Yeah, that's a great question. I should have put that one in because that would have been a lot different than the rest of these. Yes, because partly of the chemistry angle and the resolved stratosphere. Yeah, it's been used for paleoclimate. It's been used, for example, effectively to show that CESM2's climate sensitivity is not consistent with paleoclimate, so it's just too high. There's some studies folks have done from the paleoclimate group at NCAR, I know, using WACCM, and then I know some folks at the UW, University of Washington with Chong Fu have used it to look at ozone chemistry in paleoclimate. So yeah, it's been used for that, but yeah, this is obviously very expensive. Actually, the 2-degree model is maybe what was used often for those because it's a little more economical.
I was going to say, I know for lots of paleo simulations, the 2-degree model is used just because when you're running thousands and thousands and thousands of years, it adds up.
Yeah.
Hi, thank you for the excellent presentation. I was wondering if the changing from CAM to WACCM gives any added value to the study of extremes like extreme weather events.
Yeah, I mean, it depends. I mean, I might think that if you're talking about like mesoscale type stuff, that's probably where if there's a benefit, it's really small, unless something really matters about perfectly resolving the tropopause. It's really more like the larger scale stuff. Like I think, you know, if you talk about like large heat waves, which have a big upper tropospheric weight to them from high pressure systems, maybe there's some strat-trop coupling that could matter there. I'm just aware that the cold air outbreaks mostly. That's mostly the cold extremes in winter are usually the one people point to. Yeah.
All right, last call. Scanning the room. Okay. All right, well, thank you so much, Nick.
Thanks.
So we'll go to our first break. It is, sorry, I believe it's 9:15 right now. So come back in here just a minute or two before 9:30. So take a little break and we'll see you back.
it work?
Okay.
Yeah.
Yep, I think. So we're going to go ahead and get started with the next lecture. Next, we have Simone Tilms, who also is in the ACOM lab of NCAR. So that's the Atmospheric Chemistry Observations and Modeling. I was going to say, if we have other conversations, could we take them outside so we can go ahead and have this?
Nick.
Okay. So we have Simone Tilms, who's going to talk to us more about how chemistry is done in the atmospheric model. She's part of ACOM, and she studies chemistry, aerosols, and has done a lot with geoengineering. And she's also the co-chair for the chemistry working group in CESM.
Okay, yeah, welcome everybody. And I'm so excited to see you all here in person. It's great. And I also wanted to say so I'm the co-chair for the Chemistry Climate Working Group. We also have Rafael Fernandez as a outside co-chair. We have a software engineer, Francis Fitt, and our Chem liaison is Rebecca Buchholz, who is somewhere there. And you will talk to her more on Friday when you do your exercises. So I want to talk about chemistry and aerosols in the modeling. And I wonder who is actually interested in chemistry and WACCM in this group. Who's going to do the tutorial? Because then we have about an idea how many people. Okay, great. Yeah, but even though you are not going to plan to run explicitly chemistry or aerosols, you need to listen to this talk and the lecture because it's important for all of the different the atmospheric configurations, because all the configurations include aerosols and include chemistry in different complexity. But I first want to give some motivation. Why do we care about chemistry and aerosols? Well, this is from the recent IPCC report. This is the increase in effective radiative forcing since the 19th century. And what you can see is that the effective radiative forcing is mostly driven, which I think is shown in the black line, is mostly driven, obviously, by CO2. With increasing CO2, we have a increasing radiative forcing. But then there are other very important parts to it. On the one hand, it's these really big spikes. That's the stratospheric aerosols coming from volcanoes. If we have a large volcanic eruption, like in 1991, you see a strong reduction in this forcing, which is the cooling in the stratosphere. But then there are other things, like other chemistry. We have methane. This is a short-lived climate forcer, which has a substantial amount of adds to the radiative forcings, but also nitrous dioxide and also ozone. And if you would add up those, they make up about a third of this radiative forcing. So they are important. And the other thing is, of course, the tropospheric aerosol. And you see here in this line, the tropospheric aerosols actually cool the climate. With increasing pollution and increasing aerosols in the troposphere, will actually counter the effect of the greenhouse gases and mask the warming. So you can understand that if we're actually going to clean up some of the aerosols, we'll get a warming just from that. So they are important, but they have a large uncertainty, as you can see in that error bar. And so it is really important when we want to really look at climate that we simulate chemistry and aerosols in the climate system and doing it well and not being completely off, even though there's a large uncertainty. And this is just translating it now to also effective radiative forcing. This is the difference from 1750 to 2019, again from the IPCC report. And again, CO2, greenhouse gases are very important for the radiative forcing. But again, these other emissions from N2O, halogens, NOx, and so on, contribute substantially. And some have this positive forcing, and those that lead to actually increasing aerosols, as I showed, result in a negative forcing, like SO2 forming sulfates, and therefore partly cooling the climate. And this is important for temperature, as I said. So this is just another view of what I said before. And again, like ozone, this is a chemistry that is acting in different ways depending on where they act, like in the stratosphere, in the troposphere, can be positive or negative. Large uncertainties again here in what the aerosols do. So now let's go a little bit, why is chemistry else important? It is important for climate, but it's also important for air quality. And those people that are living, I mean, even here in the US, wherever you are, you know that there is effects of air quality. You hear about ozone pollution at the troposphere, and ozone pollution is coming from traffic, from industry, private use, and farmlands, and so on. And ozone is bad. If we in the troposphere increase ozone levels, it damages our tissues, the respiratory tract, causing inflammation and so on. And so there are problems with that. But then also people are maybe more aware of particle matter is important, and that's due to increases of aerosols. We have our different precursors that are emitted, and we'll talk about it a little more how it's described in the model. So this is also from farmland, from traffic, industry, and then from fires, right? Recent weeks, we see the effects of fires. It's really bad for us. And then there is dust in many other places than maybe here, but in more in the global south and in the tropics, dust storms are very important. Volcanoes, outgassing volcanoes, they are a big, it can cause hazards and increases in air pollution. And again, this can cause various problems, and some of you studying air quality quite aware of this, and there are actually quite many people impacted by this, which is expected to get worse in the future. So in general, simulation of atmospheric composition is in this figure nicely shown. It's actually not only a local effect like I showed for the air quality, right? We have the sources that are at the surface often, but actually shown here, the sources will actually go up in the troposphere, in the mid to upper troposphere, and then they get transported. Like fires in some places, you know, from Canada, they come over to the US because it's not local. And that's why it matters for many places in the world. It's not just like, okay, well, we can do locally something for us. It does matter somewhere else. The transport is important. It needs to be resolved properly. And you heard a lot about dynamics in the last few days. But now also we are looking more at the chemistry. It is also important that aerosols and chemistry goes up into the stratosphere and impacts, obviously, the ozone layer we heard before. It impacts the stratospheric background distribution, and then coming back to climate. So just one more slide, and I think Nick clearly mentioned and talked about stratospheric ozone, but that's also important. Even for air quality, Nick showed that the stratosphere is important due to the dynamics, because it will go down and change some of the tropospheric circulation. But ozone in the stratosphere is also impacting even all the way the air quality. If we have a lot of changes in the stratosphere, or it will, through trop-strat exchange, can impact air quality. But ozone, of course, is also in the stratosphere very important for us, for life on Earth, because it protects us. It filters out UVC, which is a very dangerous radiation, but it also partly filters out UVB, and then directly impacts how much radiation actually comes to the surface and impacts us. If we have changes, like due to the ozone hole, as Nick has described, we will get increases in cancer or cataract or other impacts. The ecosystems are impacted by changes. So it does matter. It does matter how we simulate it and what the impacts are also for plants and other things. So what I want to do now, after this motivation, is discuss a little bit how do we describe chemistry and aerosols in the model. And I go through a little bit the processes that we are describing. And you will find some of these things when you do your exercises, even if you don't run a full chemistry model, as I said before. And so basically, when we look at a component, at each time step, in each model grid, basically, what the concentration changes are is a combined effect of the production of the component and the loss. And those can be described of the emissions that come in, then the chemistry we are producing or changing gases and aerosols. And then we have gas to aerosol exchange processes. And of course, advection and diffusion out or inside the grid box, cloud processes. But with that, the clouds will be impacted by the aerosols, but also gases will go into clouds and get changed to aerosols and then get removed through wet removal and then dry deposition. And so it also depends on how you actually do those processes, in what order you do it. And I'm not going into the details. There's a lot of discussion on how things are reordered right now in the model. But it matters, and it's important to understand this. And this is just a view of the life cycle to illustrate it for you a little bit, and then I'm going through those different components. So we have the surface, and the surface will provide emissions from the biosphere. And then it also provides emissions that we have to give the model, which are the anthropogenic and the biomass burning emissions. So we, at the moment, don't interactively have fire emissions that go into the atmosphere and change things. We are prescribing those emissions. And then we have emissions that are vertically distributed, like from aircraft. Again, we're prescribing those emissions that will go and into the model. We also have things that automatically get calculated, like lightning NOx. The clouds produce NOx, actually, and that impacts the chemistry. So that's important. And then we have the chemistry that will go through. Then we have radiation that will interact with the chemistry. We get heating, we get advection that causes also movements and dynamics in the atmosphere. And then we have the cloud processes and wet removal. And also there's the dry deposition, which depends on the land and other effects. So we'll go through this a bit step by step and how it's described in the model. So first, surface emission and concentrations. So we have two types of basically what we call sources. One is the emissions, the surface emissions that are described, as I said, this is anthropogenic emissions. Often we have inventories of anthropogenic emissions, like the CMAP6 inventories that tell you how much of what gas in a rate of emission will get into the model at the surface, as I said before. So you have biogenic, biomass burning, ocean, soil, and so on. But then there are the vertical emissions, as I said before, aircraft, volcanoes, power plants. In the model, when you see that, it's called external forcings. That's how we call it. So if we see external forcings, that's vertical emissions. And then one thing we do is also surface concentrations. And in the model, in the name, let's call it lower boundary conditions. And that's when we set greenhouse gases to fixed concentrations. So, you know, CO2 is very hard to simulate. I don't know if you had a lecture on biogeochemistry, but so we want to constrain it, and you probably heard it. So at least in some model simulation, in most model simulations, these concentrations are constrained and fixed at the lower boundary condition, so at the surface, and then the atmosphere will do some chemistry anyways, or maybe set it to a fixed value depending on the complexity. So this is an example of surface emissions. As I said before, you can see this is, for example, NOx. And this includes all these kind of emissions that you have to describe more or less in detail in your model version. For example, if you run with chemistry, you have to describe surface emission of NOx. If you run with very simple chemistry, you may not have those because they are described differently, and I will go over that later. This is an example of the lower boundary conditions, the fixed greenhouse gases. Here shown here, for example, it's just an example on the changes that we're imposing, for instance, for a high forcing scenario in CMAP6. And then the chlorofluorocarbons that matter for the ozone hole. Oops, sorry. Yeah, so they are prescribed, but they can also matter. It can also sometimes change with latitude because, you know, it's not usually one number. Sometimes we impose some kind of latitudinal dependency on those because you have more concentration in the northern hemisphere than in the southern hemisphere and so on. Now coming to the chemical mechanism. And actually, I need to see, yeah. So chemical mechanism, as I said, you can run with very different complexity in the model. We're trying in the ChemChem version and also in the full chemistry WACCM version to really have a very comprehensive chemical mechanism, and reactions are over 500 reactions. I'll go over that later. But so that includes various things that are important in the atmosphere to really process and form ozone, methane, and other important gases. So we have photochemistry included, we have gas phase chemistry, heterogeneous chemistry, aqueous phase chemistry, meaning chemistry that happens in clouds, and gas to aerosol exchange. We also have stratospheric chemistry. Nick had alluded to it a little bit. So we really include complex chemistry that we can simulate things like the ozone in the stratosphere, the ozone hole that has been evolved in, from the 80s on. And you can actually see here how the ozone hole has developed from starting about in 1970 towards now, and we're still here at the minimum of total ozone. So we haven't seen much of a recovery yet, but due to the phase out of the CFCs, we hope to see a recovery in the future. Those things need to be included and are included in all of our, in all the comprehensive full chemistry mechanisms for the stratosphere. And so here it is. I think Nick showed it briefly. So we have different chemical mechanisms depending on what atmospheric model you want to use. For the WACCM model, we have the troposphere, stratosphere, mesosphere, and thermosphere version, which has the largest amount of solutions and reactions. We have the TS1, which is the tropospheric version, the troposphere chemistry version. So if you run ChemChem with a 40-kilometer lit, you don't need actually the ionosphere stuff, but it's not very much. So most of the chemistry is still included in the 40-kilometer top model. So you do actually simulate ozone quite well, but not as well as Nick was saying, because you may not have all the complexity of the dynamics in this. And so we have a lot of also different mechanisms. At the moment, we have also a TS2. If you're more interested in even more organic chemistry, there are different versions of the model. If you're interested, let us know, and we can tell you more about that. We have this middle atmosphere chemistry, and again, that's really mostly the stratosphere chemistry, making sure ozone in the stratosphere is produced properly. But we are not caring so much, as Nick said, about in the troposphere, and the air quality. So actually, don't use it for air quality because it's not well represented at the moment. And that's really important because some people do still look at things like ozone or surface ozone, but that's not a model to use it for. And then there are different flavors, also the prescribed chemistry in WACCM. You can run WACCM really with very simplified chemistry, very similar to chem. And I want to show also a little bit of a difference between chem and chem in regard to chemistry and aerosols. So chem only really uses much fewer chemical species, and it also fewer reactions, because we want to run it for a long time. We want to make it cheap, but we therefore also missing some of the complex chemistry. But how do we do this? So usually what we do, we use like a ChemChem or WACCM model that produces us a full set of chemistry. Right? Like we run from a historical simulation from 1950 to 2010 or 15, and we derive all those chemistry fields. And then for chem, what we do, we take those fields actually from a WACCM model run and produce a prescribed field. So we can then use that in chem. So it will be consistent throughout the two models, but it's not interactive. So what we do is we are basically using prescribed fields that we get from WACCM or ChemChem and have very few interactive chemistry fields, mostly for the purpose of describing the aerosols properly. Because aerosols in both the chem and the chem-chem models in the troposphere are represented in the same way. I come to it in the next slide, or in a couple slides. But for the chemistry, we really have prescribed ozone. We have prescribed ozone in the stratosphere. We have prescribed ozone, aerosols in the stratosphere. And then we have these oxidants in the troposphere and the stratosphere and other things. Okay, so we also have very simple secondary organic aerosol chemistry. And in the current model version, actually, we do have some differences as a result of the simplification. We have a newest version. If you go forward with more recent model versions, we have done some fixes to improve actually the simple chemistry version that also the aerosols look a bit more similar compared to the full chemistry version. And then the aerosols. So our default model is the modal aerosol model. And if you look at aerosols in the atmosphere, you can usually describe the distribution of aerosols in form of modes. So instead of describing all the complexity of sizes of aerosols, what people came up with is this modal distribution. And so you can have some modes going from the icon, the small mode, towards the so-called accumulation mode, and then the coarse mode. And so we, in many climate models these days, you use this modal distribution because you basically don't have to keep track of all the aerosols in different sizes, but you only have to keep track of the different modes. And of course, the distribution and aerosols within those modes. But one thing that will occur to you when you actually look at the aerosols weirdly, and it's just something that happened, is that the lowest mode is actually the A2 mode. So if you have sulfate, it's called SO4A2. That's the smallest mode. And the accumulation mode is the A1 mode, and the coarse mode is the A3 mode. So just something to keep in mind, sometimes that confuses people. We also have a fourth mode, which is also not the bigger even mode, but that's the primary carbon mode because that was added later on. That is basically a mode for black carbon and organic matter to describe an aging process that wasn't in a previous version of MEM4. So you can read about this more in different papers. But all those modes, different modes with different aerosols included, they are internally mixed. So basically, we are transporting the modes, and aerosols will evolve within. And then there's another description, which is the karma model, which is a new model, the sectional aerosol model. I don't have a slide on it because we don't have it officially supported at the moment in any ComSets. But if you're interested in that, you can talk to me, and we do have some version that people may be using already if they're interested. So then secondary organic aerosols are very important in the climate system because they are important for forming organic aerosols. Organic aerosols are important for climate, for air quality. And we do have a very comprehensive way of describing these aerosols if we have the full chemistry version. However, if you run with the prescribed chemistry version, we do something very simple. And there are differences, as I said before, that may impact the climate. But in recent efforts, we have improved some of that. Going to the aerosol cloud now, and actually, I don't know, how long do I have? Till 10, is that right? Yeah. Sorry, 7 more minutes. Okay, good. Yeah, so aerosol cloud interactions. This is complicated, and this is actually taken from a paper from Wang et al. That is from the E3SM model, which in a way, it has very, very similar processes as we have in CESM. And as you can see, what we are describing is both convective clouds as well as stratiform clouds. And to form clouds, you need aerosols. You basically need an aerosol precursor that will then activate, and you get cloud droplets. And then these clouds, of course, form with various dynamics. And you have heard about it and understand it much better than I now. But so you have convective updraft, you have secondary activation, you have ice nucleation, snow formation. All of these processes are included, and you can imagine aerosols will get forming the clouds. If clouds evaporate, the aerosols will get released again. So this is in the model and is described. Then also somewhat different is the stratiform clouds. They have different processes included, and then the wet removal as well. So it's, a very, very interesting paper if you really want to learn more about this. Then dry deposition, going back. Now we had wet deposition, wet removal in clouds, at least somewhat. For dry deposition, we do an interesting approach, which is like a parallel approach and a resistance approach, basically, that you do have some parallel as well as linear connected resistors that described what your velocity is and how much you remove a certain concentration or particle. So this is shown here. It depends on various things like the sublayers in the atmosphere, the interfacial sublayers, vegetational sublayers, and then also depends on the specific of the surface. So this is done in the land model, but it gives the information to the atmospheric model so we know how much of the concentration we have to actually remove. And for wet deposition, this is also done, as I said. We do have the clouds, we do have ice, we have rain. Those get removed. And there's a rather simplistic approach, which is shown here, which is there's a fraction in the grid box that the tracer has to be removed through a certain loss rate. I want to give one example before I finish, and I could have given more. This is what I said. Chem, full chemistry is a lot used for air quality studies. And what we're also using is the nudging, as Nick has described before. We try to represent, a certain, say, pollution event. We want to try to simulate something what aircraft campaigns are showing. And so we run the model usually in a 1 degree resolution. But there is also, and there was a question about the option for regional refinement. And so we have developed the multi-scale infrastructure for chemistry and aerosols framework, which is basically when we use chem with a regional refined dynamical core, which can also be WACCM or other can be chem. But basically, we do a refinement over a certain region. As you can see here, this is over the Conus region. We have a 100-kilometer outside grid, and then we do have inside up to 14-kilometer resolution. What you can see here is surface ozone. And you do actually get a much better representation of surface ozone when you have a higher resolution, because chemistry often happens in a much smaller scale than in 100 kilometers. You have point sources. You have also changes in removal. And so you do see something that represents, well, not shown here, but it does represent the data in cases better if you have regional refinement. The other thing and an advantage of this is that we can actually see that there are differences in the long-range transport as well. I talked about the long-range transport. If you change your sources and the chemistry, you're also going to change somewhat the global ozone or other chemistry in other places. And with this, I just want to point you to our support page. So we do have the bulletin board. You have already heard about it. In particular, for chemistry, we have a wiki page, which is the ChemChem wiki. And here is an example or part of this. So what you learn in this tutorial is, a start. But if you want to learn more, and if you want to be engaged in ChemChem and also WACCM, we do have a page, and especially Rebecca is maintaining it quite well, with updates, with more complicated advanced changes, and also with user community, with support and other links. So this is a very helpful resource, I think, for even when you just want to run chem, to see if you want to do some changes. Maybe there are other things coming up in the future. We haven't talked about it, but emissions, how they are described now, may change in the future. We may have an interactive scheme that is called HEMCO that will be very different from what we are doing right now with emissions, and you can learn about those things. So this helps you keep track of updates. The other thing is our Musica, this wiki. And that's also helpful for creating regional refined grids, for creating your own grid, first of all, but then also a lot of support on how to run it. We had a tutorial set up with different stages of how to create your own grid, how to run the model, but also how to look at output with some Python code bases that may be quite helpful for people. Yeah, and with that, I thank you and be happy to answer any questions. Thank you.
All right. Thank you, Simone. Okay, so thanks. And let's go ahead and I'll walk around for questions. So we got first one here.
Thank you, Rebecca. That was a great presentation. So I'm interested in asking about the prognostic equation that you mentioned in one of the earlier slides. So if we speak of tropospheric aerosols and the way they react, and stratospheric aerosols, so there is a difference in time scales. So I was wondering whether that equation was more of a generalized equation, or for troposphere and stratosphere it will be slightly different. And whether you have any more slides or anything to say about how the aerosols interact with the cloud microphysics, because you showed a diagram, very detailed diagram for convective and stratiform rainfall and how aerosols interact with that. So how the different components contribute for different type of ice hydrometeors and cloud ice, cloud water. So do you have any slide on the prognostic equations or anything to say?
Okay, so the first question on the stratospheric aerosol and the tropospheric aerosol. So yeah, we are actually with the full chemistry version, and I didn't say that, but we do simulate both interactively the tropospheric aerosols and the stratospheric aerosols. So in the troposphere, we do, as I showed, have the emissions, and we have the formation of the aerosols and the transport. In the stratosphere, we do also have formation of aerosols due, sources like DMS or other sulfur species. So sulfate is a very important aerosol in the stratosphere. And if we have explosive volcanoes or do geoengineering, we can actually, from precursor emission from SO2, form aerosols. And from the time step, while they may have different time steps, we do have our model time steps, so they will be just calculated in that way. And if you do change, though, the dynamical resolution, then you change your time step. But we're not changing the chemical time step in the stratosphere and the troposphere. But we have, of course, different reactions that matter in the different places. For the wet removal and for the aerosol cloud interactions, I didn't bring any equations, right? So it's quite complicated. And there were, in recent years, some updates on the wet removal scheme and convective wet removal. We also, it depends on what schemes you have for cloud activation, depending on what aerosol sizes you're using. So I think, I don't know if it makes sense to, I didn't bring any equations, but you can read up on this. There is our, first of all, the CSM documentation for Chem 6 that shows a lot of nice updates. The paper that I was showing actually gives some updates, and I can also send you some recent updates on that if you're interested.
Before the next question, I was just going to say there's so much documentation for CESM online, especially compared to many other Earth system models. And part of the reason we don't get into like all the equations in this is that we know different groups of you or each of you is interested in different things. And so the people who are interested in the ocean primarily, when it's too much into the weeds of these models, then you kind of just zone out. So we're trying to get you the big picture of how these models work, how it all works together. And I will say from personal experience, I've done sea ice stuff and you find something weird in the sea ice and then I trace it back and I find out it has to do with the clouds and the aerosols in the clouds. And so this is why we all talk together, because I don't feel like I know that part very well. So then I've collaborated with Simone and been like, what is going on here? So yes, all right, we have another question back there.
Thanks. I was wondering if you could talk a little bit more about how the prescribed fluxes between the land emissions and the atmosphere, like for example, the biomass burning emissions, like how do you derive or decide what the parameters are for the prescribed parameters?
So usually for anthropogenic and biomass burning, they are inventories. So people spend a lot of time figuring out actually what is the amount of biomass burning, fires we get into the model, and it's not easy. And actually, Rebecca is she's much more an expert in that. Actually, you use satellite data, you look at fire counts, you use various things, but there are different inventories and different approaches. And please go and ask Rebecca on all those details. But, it's actually not clear. If you look at different inventories, you get different answers. So there's large uncertainties on that as well. We try to constrain it. You have also emission factors because you scaled, say, from CO emissions to different chemistry. And this is something that you can make choices. You have to make choices that can lead to uncertainties. They're not so easy. For biomass burning, what we can do, actually the land model does derive fire emissions. And there are versions if you look online, that you can actually turn on interactive fire emissions, so you get emissions, because they are calculated, they go actually in the atmosphere and do that. And we tried out those things, but they are not really scientifically supported at this point. So you have to be careful when you try out those emissions. We have started some actually climate run, pre-industrial control run with those emissions, which is interesting because that gives you much more interactions. The other thing, really, the fluxes, right? Coming back down, how do you describe it? And that's often done in the land. I showed it just very simply the dry deposition and other things, but it depends on various aspects on the land. And for instance, we are trying to improve like dust deposition, dust emissions, and other things in the model. So there's always work being done to improve those schemes. Yeah, I don't know, but is that good for now?
That was great, thank you.
Maybe I should say biogenic emission is another thing. We're interactively actually getting from the land emissions from the biosphere, which helps for like formation of aerosol, organic aerosols, and so on. That's in the full chemistry version. We have some simplified approach at the moment for chem with no chemistry, but we'll also tried in the recent newest development version to couple that more. So it will be more interactive as well.
Thank you, Simon. Very nice talk. I have a question about aerosol cloud interactions. Does model consider the cirrus cloud?
Cirrus cloud, yes. We do have also cirrus clouds. So we have mixed phase clouds, ice clouds, and cirrus clouds. And so there are parameterizations out there. And we do have, at the moment in CHIM 6, aerosols impact the cirrus clouds and change them as well.
Hi, Simone. How easy is it to sort of mess around with the chemical mechanisms in CSM? That's something that I'd be quite interested in doing.
Yeah, you will. On Friday, if you want to do the chemistry, we will just show you what the chemical mechanism looks like and how you can actually change it. So basically, we do have a chemical mechanism file that has all the reactions. And simply you can go in and change some reaction rates. You can change things. But it's not quite that easy because we have also more hard-coded reaction rates for some things that are more complicated. So we have a preprocessor. Basically, you have a fixed chemistry. It calculates all the reactions and makes new programs that the model then uses. So if you change the chemistry, it will create a new set of programs that you then run the model with. It becomes a little bit more complicated if you add chemistry. If you want to do very complicated new chemistry, you have to add the emissions. You have to make sure you know what the reaction rates are. You need to know what the deposition is, what's the Henry's law coefficients or other things. But it's actually not that hard to do. So yeah, you can play. Yeah, whatever you wish.
All right, who has the next question?
Hi, I had a question about Musica. So I was wondering, what is the model height on that? So like, does it resolve the stratosphere, and could you use it for SAI stratospheric aerosol injection experiments?
Yeah, so Musica, in a way, I mean, at the moment, what Musica is really chem, and it can be also, Musica is a framework, right? You can use different atmospheric dynamical cores, different height of the model, different resolution. What we defined as Musica version 0 was a chem version that was a 40-kilometer top. And you could do a regional refinement in the stratosphere and inject aerosols or gases there and run it. We haven't done that. It's a very interesting experiment. But what do you miss out if you have 40 kilometers? Well, Nick explained that, right? You may not get the full dynamical a distribution, but maybe what your purposes is fine. So often it still is quite a bit of a question for stratospheric aerosol injections or other things. What model top is actually a reasonable one? It really depends often on the science question that you're asking. But yes, you could use it, and yeah, happy to talk to you more if you want to do that.
Hi, thanks for a great talk. I have a question on the vertical emissions files.
Yeah.
So are those represented in different attitudes? But how is the power plant being represented? Are those regional or like global?
Yeah, so the external forcings, how we call them, they really are, it's a file, that is a three-dimensional file, and of course with time, but you have an altitude and you place your emissions. So you can make your own vertical emissions and place like aerosols or gases, and then the model will read it and interpolate actually to the model grid. And so what we do for power plants is that we assume that usually we have just simply SO2 emission from industry, and we do have power plants, but you think that the stack is a little higher than just at the surface. So we'll take a tiny little amount of the gas, like 2.5%, and distribute that as an aerosol in the vertical, for example. So, and as well, we can do that for SO2 as well. But so we represent some of the aerosol at a higher altitude, and we get a little bit different distribution.
Okay, thank you very much for this great presentation. My question mainly related to the emission inventory. Do you have emission inventory for Africa? So and what resolution?
Yeah, there was actually, so our emission inventory that we're using for CMIP is pretty, maybe not that good for Africa, right? You may know that. Then we have the camps or something that often, Africa, there are sources and things that haven't been represented. There is an inventory that had been created. But I don't think that, I don't know, Rebecca, maybe you know if we have it in our list of inventories. We had done some test runs with some, but I guess I have to refer you to some like Forest, Leslie, or
That will be great, especially if we are, okay.
Maybe you can say more.
Hi, I'll just add some comments. There was the African emissions dice.
Yeah, that one, the
was
dice
created.
one, yes.
Yeah, so I think that might be described on the wiki. We might have information about how to use that, or yeah, Forrest Lacey definitely is someone to talk to who developed that. And then generally, our emission inventories are global. Yeah, so we have the global like CMIP 6 emission inventories and the CAMs in terms of anthropogenic, and the same for biomass burning.
Okay,
Yeah.
do you think that is it easy to develop emission inventory for a specific region in Africa?
Well, people
We can do that also.
Yeah, you
She's
know that's-
nodding. Yes.
Yeah.
Yeah, the short answer is yes, you can develop it. It's just you need to, develop it through aircraft emissions, through other emissions, and so on. People have worked on it. It's a lot of work. If you do have an inventory over some region, you have to make sure that you kind of put it into the global inventory too. So you have to take some out, put some in. It's a bit of work, but it's possible, yes.
Yeah, okay, thank you.
All right. There.
Hi, just going back to the biogenic emissions, you mentioned the coupling between the land and the atmosphere, but is there also coupling with the ocean? Because my understanding is that like DMS production is often constrained by dust deposition and temperature.
Yeah, so what we did in the version you're going to use, it's like just the prescribed DMS emissions from the ocean, but now we actually had C1, what's his last name? Yeah, put in a machine learning approach emission data set, basically. So now the DMS emissions are actually interactive, depending on specific of the ocean temperature and whatever is required for that part. So yeah, we do now, in the newest versions of the model, actually have interactive DMS emissions.
Thanks.
All right. I think we have time for one more. So who wants to ask the last question? All right.
Thank you for your talk. I was wondering what your opinion is on how government and industry respond to climate science, and then also how that impacts the science that is undertaken and the scientists themselves. And I'm asking that sort of in the context of climate geoengineering.
How governments does what? I didn't understand the first
How
part.
government and industry responds to the science and how that impacts the science that is undertaken. If you have an opinion, if that's too much of a loaded or strange question, then feel free to say no comment.
I wish the government would respond to science more. That's my comment. Yes. I think that would be great. For the short question, yeah, maybe much longer discussion.
Maybe that's a break discussion.
Yes.
Speaking of which, we're at the break. Before we go, Elizabeth wants to make an announcement.
Yeah, just a few instructions or guidance about break today. So we've got yogurt on the side table against the wall. There's dairy and non-dairy. And then we've got bagels cut into reasonably bite-sized pieces. And they're on the center table, and the toppings are on a third table. So I spread things out a little, hopefully to expedite. And if we could just maybe choose a yogurt or a bagel first, and then see how quantities go today, that'd be awesome. Thank you.
All right. Thanks so much. You have 15 minutes, so I think we'll be back here. Thank you so much, Simone. And we will meet back here at 10:30. All right, so welcome back from the break. We're about to start our morning lab session. Cecile here is our model runner extraordinaire. I feel like she knows how to do all sorts of model run things that I don't, and she's going to lead us through this set of exercises and give you a little introduction.
Then, can you hear? Okay. Okay, then this is the introduction to the practical for today. And what we are going to cover in the practical this morning and this afternoon, we are going to learn about how to do name list modification. Then we are going to learn how to troubleshoot when the model crash. And I know some of you already did this yesterday, and then we will also learn how to do code modification, then to modify CSM. Then something that I want to say before, it's a quote from the matrix, but I can only show you the door, and you are the one that has to work through it. Then basically what I want to say here, I can talk about CSM for probably hours and hours and hours, and then you will leave the room and you will have not learned anything. And I think it's really when you go with your little finger and you do this, then you are going to learn. No, but it's really true. You laugh, but it's really true. Then, to cover this, instead of me talking, I'm going to barely talk here. I like to talk, but I'm going to refrain. Then you will go on the tutorial webpage, and then we are going to cover the section that are there in blue. Okay? Then everything is self-explanatory. Then I'm going to just give you a little bit more information. Then first, the name list modification. What are name lists? How to modify them? For example, let's say that you want, of course, somebody is calling me. For example, you want to change the output frequency of the model because by default, the model for most of the components give you monthly mean. But let's say you want to look at the daily cycle. It's not useful. We are going to learn how to do this today. Then how are you going to do this? Then you go to this web page, and I'm going to ask you, this is the structure for name list modification. There is an overview. They explain you where to find documentation, how to customize the output, and then there is the exercise. Then go step by step in this chapter. If there is something that's not clear, it's the first time that we put this documentation online. Let me know. This is not because of you, it's because of me. Then we want to know if it's something that's not clear. And you will go through this. The second step, it's troubleshooting runtime error. And some of you yesterday at Crash, and I show you already a little bit how to look at the log file, but it's some clue how to find information about the crash. And it's not always easy. I do this all the time, and often I look like this. But it's really not. It's not always easy. But the more you do it, the more you are going to learn. And then there's different way to do it. Either you are like me, you have been working here for 20 years, and you have a lot of good friends that are much smarter than you. Then I ask them. But if you don't have worked here for 20 years, then there are some procedure. Then you look at the log file. You can add debugging info. You did this. Some of you did this already yesterday. Then again, go through this section step by step. And then if it's not clear, please let me know, or let Alice know. Last thing, then you are bored, and now you want to move to the next level, and you want to modify CSM. Then, for example, in this case, we will add a variable in the atmospheric model. Then when you do this, then again, a quote from the matrix, it's your choice, the red pill and the blue pill. And basically, in the movie, the first movie, then the main character is for the choice between the red pill and the blue pill. And basically, the blue pill, I think it's really described the situation. The blue pill allows him to remain in the matrix, which is a fictional computer-generated world, and basically CSM. And the red pill, it leads to the escape from the matrix into the real world and embracing sometimes the painful truth of reality. Then once you try to modify the model, you are going to run into a lot of issue. But on the other hand, it's really fun to do. I love to do this. I take the red pill very often, and I like it. Then this is basically, sorry, I guess I'm a clown. This is basically, again, you go through the chapter, If you don't understand, what do? You ask, and you tell me, this is not clear, I want you to fix this. Then, okay, ask me or anybody else in the room. Okay, then.
If you do that, please do it constructively and kindly, though.
Yeah. I'm very mean, you know. No, I would like feedback. Then, some question that I'm sure you have. She wants me to move to this, and I haven't even finished my Monday exercise. What should I do? Okay, then I want to remind you that this is not a race, a rat race. This is really like something that you learn. You should not compare you to your neighbor that maybe has already finished the tutorial or something. It just, you come with different experience and you move at your own space. And then it's really how you are going to learn about CSM. And the more you crash the model, the more you are going to learn. Then when everything goes fine, you don't learn anything, unfortunately. You can have the other situation. I have already completed all this exercise yesterday. What should I do? Then you can continue to move. Also, you can help each other. I saw this already. I found it was amazing. You are amazing. I found an amazing group. And then I saw people yesterday that will explain to each other. On Monday, we had some problem with what was the problem? We had a problem with the queue. Then I saw people. I explained to one person and then another person. And I saw people started to explain to their neighbor. Then it's what we want you to do because it's really, and a lot of people are talking to each other. But if you prefer also to work on your own, it's fine. It's just like everybody learn differently then this is, but you can, there is always something to do. Then you can become a helper once you have finished everything. There are a lot of exercise also at the end that you can do. And then the last thing, because it was something that has come up, I'm completely confused about the tutorial special queue, what should I do? Then we put with Alice, we put some documentation online. Then if you have here resources, NCAR HPC environment, then this is for today, but it will be for the other day. It is like coding. If we are Wednesday from 10:30 to 12, what do? You do XML change queue, this number -4. I hope I didn't screw up in the number. No, it's good.
I think you
then,
can't have
if
the
you
space.
are
You can't have the space there, I think.
Sorry?
There are spaces here. I think that will give you an
okay.
error.
No space, Yeah, sorry. Then basically you do the XML change. Yeah, I will fix this right now. Then otherwise you do the job queue this. And then if you are at any other time on Wednesday or any other day, you do job regular. Because otherwise, if you are not in this time, you will not have the special queue. Does it make sense? This special queue is just something, the special queue is just something to make stuff faster, that you skip the line in front of everybody, then this is the purpose, but the regular queue should work too. Yes?
If it's like 11:55, should we just submit to the regular because it's unlikely that your model will be like getting through the queue at that time?
Yeah, because if the job start in, it's a really good question. If the job start in the special queue and then you hit 12, it crash. And then it's good because you can use my debugging exercise, but it's just like, And you might also, I think Alice probably you told you this. I know yesterday some of you started the long run, and we have currently, Cheyenne is like a very old, I don't know if it's a man or a lady. What's the computer? Then it's a very old computer. And then it started to have a lot of issue. Then we are getting a new computer soon, but the problem it's not there yet. Then you might, the longer the run you do, the more problem that you are likely to hit an issue with Cheyenne. They are fixing stuff at the beginning of August, but unfortunately, it's not for this tutorial. And there will be a new machine coming soon then.
But fortunately, the computer is up this week instead of them taking it all down.
Yeah. But but I can tell you, I had like many erratic crash not due to my run in the last few days. On Saturday, I stopped counting at 20 crash. Then this is question. This is a picture that my son did in Minecraft, and I really like it. And my son is 20, but he's just like, he still like to do Minecraft stuff. And I yet has a picture that you will have lightning coming on Anchor, and it's just like, you saw this,
yes,
I think,
but,
Alice.
but hopefully not. It's supposed to be hot today. I
Yeah,
don't think
yeah.
there's any cloud.
This is the two-day picture.
I want to make one comment as well. Could you go back one slide, Cecile? So I think we have a lot of stuff that can keep you busy with the name list, the troubleshooting, and the source mods if you're on that second FAQ. She has, I would not recommend that you start the diagnostics today. We're going to try to do that tomorrow. But you'll notice that something's different on these queues, and that's for Thursday, our reservations on Casper instead of Cheyenne. And that's because we're doing diagnostics instead. And so not that you couldn't run them today, but I think it would be more efficient for you just to do that tomorrow. That also means that tomorrow, if you're going to submit jobs from the exercises today, we don't have a reservation tomorrow, so you just have to use the regular queue. But if you truly get through all of these and you feel like you didn't have any questions, then come talk to me or Cecile, and we'll make you an honorary helper in training. And like she said, we'll see if you can help us help other people. I also wanted to point out that today's exercises don't depend on yesterday's. So you should be able to start today's, and then if you have more time this afternoon and you need to try to, finish the XML modifications, you can do that in the afternoon session. But I would kind of start maybe with this and see how you get along, and then maybe you can ping between them.
But if you haven't done Monday yet, then I think Monday they should.
That's right. I just wanted to point out there's
But
no
yeah,
dependency on the source mods or the nameless mods exercises from yesterday. So we're trying to make them independent exercises, but we're learning this year.
So if you are not specifying any job queue, so by default it will go to regular.
It will go in regular.
So no need to specify this job queue regular.
You don't. This is, you have to change it if you have. For example, let's say you are in the afternoon and you have done the. I'm not going to touch the screen because I know they don't like it. Then when you have the job queue, let's say that you have to change it to the second line, and then after it's almost 5, then you change it back if you submit a new job.
Okay, thanks.
But by default, if you don't do anything, it will go in the regular queue. Because it's the way, and you can look at XML query when you do a create new case, and you can do XML query job queue, and it will return regular. It's the default. Okay?
Any other questions?
Yeah, I was just wondering what the command was for the queue moves. Like if I have something sitting in regular now, but now that the special reserves are open, is there a way to move it
yes,
over?
there is a command. I don't have the syntax right now. We can add the queue.
Okay.
Yeah, we will add this. We will add this. Yeah, we can add this. I will add this to the slide. I'm going to fix this right away. Oh no, it's okay. I need to go in the. Okay, I will fix this.
We'll fix it and try to get it up there. Yeah. I try to put like something of use on this up on the screen between sessions, so we'll try to get that fixed. All right. Who else has questions? All right. I think everybody's itching to get started. So we've been trying to kind of divide you up. That's been somewhat unsuccessful, I believe. So we'll just say half the room, again, this right side, let's go to the library, or my right side, go to the library, and this left side, go to the Damon room.